I'm going to tell you a little bit about programming. And so, who of you has anyone at any time had some experience with programming yet? Okay, some people, lots of you actually. So, what programming language do you use?
I did it in Java.
Java. Oh, excellent. And you?
I did Python.
Second?
Python.
Python. Ah, okay. So I guess some of what I'm doing today will be familiar to some of you, but I'm sure that there will be new stuff for all of you. Okay, so actually what we're going to learn today is a very simple programming language, and it's sort of like a puzzle game. Okay, and it's called Alligators and Eggs. And so here, just on the slide, you can actually see what are the programming constructs that you can use in this programming language. Okay, there's essentially just three programming constructs. So we have old alligators. So these guys up there look somewhat tired, and the only thing they can actually do is they can die. Okay, nothing else. Then we have these red alligators, or these so they're called hungry alligators. So this red guy there, and so they can do more than the old alligators. So they can eat. And they can die, and they can also change color. Okay, so that's the stuff that hungry alligators can do. And finally, we have these eggs, and eggs can hatch, and they can also change color. Okay, so essentially these are the building blocks for our programs. Okay, and so the actual programs, they are families of alligators. So here is a program. It's a somewhat boring one, but anyway. So it consists of a hungry alligator, so this red guy there, and a red egg. And essentially you can think of this, so when I'm stacking them on top of each other, you can think of this red alligator sort of guarding, protecting the red egg. Okay. So here's a more complicated family. So here we have a red alligator that guards this entire family below it, and this family below is a blue alligator that is guarding the red and the blue egg. Here is a huge family. Okay, so now we have a yellow, a red, and a blue hungry alligator, and they're all protecting this entire family down here. And then there's also an old alligator here that is just protecting these two eggs. Okay, so now so far we haven't really seen anything interesting. Now, what happens? Interesting things start to happen when we put these families side by side. Okay, so just like here, so we have two families. So this one has just this yellow alligator with an egg, and here's this other family that we've seen before. And now, well, they're called hungry alligators, and there's a reason for this. So surely this one looks very hungry, and so essentially whenever you have two families side by side, and the left family has a hungry alligator, it's going to eat the family on the right. Okay, so that's what's going to happen. So this one, the red alligator now ate the yellow family. And well, they're also not the smartest creatures. These alligators, essentially, whenever they eat something, then they don't feel too well afterwards, and they're going to die. Okay, so this guy now is dying and disappears. So we're left with this family here. And now, well, so the miracle of life. So we had this red egg here, right? So it was the same color as the alligator that ate this yellow family. So what happened now is that this red egg hatched, and we just created a fresh copy of the stuff that was eaten before. Okay, so this is now the new family that we get. And well, you can see now here we have sort of the same situation again. We have a hungry alligator, and there's something to the right of the hungry alligator. And again, well, what happens is that the alligator eats this egg, and again it's going to die. And we are left with this yellow egg. So what will happen now? Yes, exactly. So we're left with the blue egg. So that's what's happened now. And well, now we are only left with this one alligator and one egg. And well, now essentially we are done because there's no hungry alligator to the left of something else. So there's nothing right to the hungry alligator up there. So now we are sort of done with our computation. Okay, so now you've already seen sort of how these how the computation in these alligator and egg programs works. Now what we're going to do is we're going to go through the actual rules that we're going to use for computing with these programs. So the first rule is the eating rule, and essentially you've already seen it, but it's a little bit more detailed than what we've watched so far. So essentially whenever we have such a, say, big family here next to each other, then we can apply the eating rule. Okay. But it's somewhat restricted, so you cannot now. So you can see there's this purple alligator at the top left that is to the left of this family protected by the red alligator, which is again to the left of this family with the yellow alligator, right? So in principle, you could think that so maybe you can actually apply the eating rule by letting the red alligator eat the yellow family, or you can let the purple alligator eat the red family. And so in these programs, only the second works. Okay, so you can only, so if you have many of these families next to each other, only the top left is the one that can eat. Okay, so here the red one cannot eat, but only the purple. Okay, so essentially what happens with the eating rule is that the top left alligator will eat the family to its right, like this. What happens when the eating rule is applied? Well, so the eating alligator dies, and then all the eggs below it that have the same color, they're going to hatch into copies of what has been eaten. Okay, so you can see here there was this family with the red and blue alligator was eaten, and so we get two copies of those from these two eggs that have the same color as the eating alligator. You can see there's still this green egg here that sort of belongs to the green alligator, and that one stays the same, so it's not going to hatch into copies. Only the eggs that have the same color. Okay, so in this previous example, so this was essentially what we ended up with after this one application of this eating rule. Okay, so now you can see how would we continue now? So can you see another application? Yes?
Green eats the yellow, and then out of the yellow.
Exactly, that's one possibility. Can you see another possibility, maybe? Yes? Right, so there's the red one. Exactly, so if you look at this family in itself, there's another, so you have like this over here. So you have this guy here, so there's this red alligator, which is sort of to the top left of this row. And this can again eat this family here. So there's sort of two rule applications that we could apply. And so the nice thing is that it doesn't really matter in which order we're going to apply them, so we can just pick one and apply the rule. So for now, let's just pick the application where we let the green one eat the yellow one. Okay, so this is what we end up with. If we go back, so this guy is going to eat this. So the green egg is going to hatch into this family. Okay, so now we have this family here, and what is the next rule application that we can do? Yes?
The top left red alligator eats
This family, right? Exactly. Now there's only one thing I haven't told you yet. So the eating rule that we're only allowed to apply this if what is eaten doesn't have any color that is sort of shared with the family that is eating. Okay, so here we have red that occurs in both families, and we have blue that occurs in both families. So before we can apply the eating rule, we have to apply the color rule. Okay, so the color rule is going to be as follows. So if we have the situation that we want to apply the eating rule, but what is eaten has some color that also appears in the family that is eating, and what we're going to do is we're first going to recolor these guys to some other color. Okay, so for instance, we're going to replace, say, red by purple and blue by light blue. Okay. So let's do it like this. And now we have, so you can see that we, so what you have to do when you apply the color rule is that you're not allowed to sort of mix the colors. So you cannot say you cannot replace both red and blue by the same color. You always have to replace them by distinct colors. And that's what we did here. So we replaced all the red stuff by purple and all the dark blue by pink. Okay, so this is now our new family. And so now we can again apply the eating rule. So now these two families, they don't share any colors, and we can just go ahead and let the red alligator eat this family here. Okay, so that's what we end up when we do this computation. So what can we do next? Anyone else? Yes?
Blue on top left is the yellow.
Exactly, so that's one possibility. Another possibility would be if this purple guy eats the blue egg. Right? So, but let's do first the thing with the blue one. So the blue eats now the yellow alligator. So this is what we end up with. And what can we do next? Yes?
The purple alligator can eat the yellow family.
Exactly, and that's the only thing we can do right now. Right? So that's because this guy here doesn't have anything to its left, to its right. Okay, so this is what we end up with, and well, again now the only thing we can do is we can let the yellow one eat the blue egg. So we do that, and we end up with just the blue egg. And now there's nothing else to do, so that we just end up with this one alligator here protecting the one egg. Okay, so now essentially we have almost seen all the rules, but remember there were also the old alligators, and so old alligators. Essentially, we can use them to somewhat group these families together. So they are similar to these hungry alligators. The only thing is, well, they are not actually hungry, so they're not going to eat. Okay. So this guy is happy now because it's sort of not going to be eaten by this one. But there's still something we could do here, right? Yes? Exactly. So here, well, this one is hungry and we can eat this one. So if you do that, that's essentially what we end up with. And now we come to the old alligator rule. And the old alligator rule says, well, if you have an old alligator that is only protecting a single family, then the old alligator dies. Okay, so here now this guy is going to die and disappear. And well, now this one is not so happy anymore. So now we can again apply the eating rule, and the blue one can eat the yellow. And we are done with ending up just with the yellow one. Alright, so that's all that we need. So essentially, we have as programming constructs, we have these hungry alligators, we have eggs, and we have old alligators. And we just have three rules that we need to apply when we compute. So we have the eating rule, we have the color rule, and we have the old alligator rule. That's it. Okay, so now what can we actually compute with these programs, right? It seems like they don't really represent anything useful, we just have these funny families. And the question is, can we actually compute anything that, say, a laptop here could actually compute? And it turns out, well, this programming language here, this alligators and eggs language, can compute everything that also my laptop could compute. So any sort of mathematical function we could compute using my laptop, you could also compute using this alligator and egg programming language. And so I'm going to show you sort of how one would show this. So how do we actually show that whatever we could actually compute, we could also compute in this very simple programming language. Okay, so before we go there, I'm just introducing a slightly more compact notation for these families that is somewhat more easier to read if these programs get a little more complicated. So if we have such a family here, and we're replacing it and sort of representing it by this kind of formula. Okay, so here you can see that the hungry alligator is represented by such a line here, and here is a variable that sort of stands for the color of that hungry alligator. Okay, so you can think of this as a hungry alligator of color X. Okay, and here's another hungry alligator of color Y. So here X corresponds to yellow, Y corresponds to red, and Z corresponds to blue. Okay, and well, otherwise you need the eggs I just represent by the variables themselves. So this is an egg of color Y, this is an egg of color Z, and an egg of color X. And you can see the old alligator is just represented by this bar here. So I'm just using this to group these guys together. So this is really just another representation of this family. Now making this still a little bit more compact. So I'm representing, whenever you have a bunch of these hungry alligators on top of each other, I'm putting them together on a single line, and then sort of just putting the colors next to each other. So this sort of represents 3 alligators on top of each other. One that has color X, another one that has color Y, and another one that has color Z. Okay. So this one thing here just represents this family here. So in particular, if I apply the eating rule with this family here, it's going to eat, so the X is going to disappear, and then this X here is going to be replaced by whatever got eaten. So it's really the same rules that also that we have in the alligator and X language. We also sort of directly apply them on these formulas here. Okay, so what you're going to compute in our language, using our language, is the factorial function. So who knows what the factorial function is? Has anyone heard of this? Quite a lot of you. So this is essentially, well, if you want to compute whether it's more likely that you're struck by a lightning or whether you win in the lottery, then you will end up using the faculty function. And so this is how this thing is defined. So it's one uses this kind of exclamation mark notation here to represent the faculty function. So this is saying n faculty. So this is a function that takes a natural number, say like 0, 1, 2, and so on, and maps it again to a natural number. So you can see here the faculty of 0 is defined as 1. So it's really, n is 0, then it's going to return 1. And if n is non-zero, then it's defined as recursively. So you can say, okay, we multiply n by faculty of n minus 1. So this is a recursive definition because I'm defining this faculty function in terms of itself. So I'm going to define it with a smaller number. This is how I'm sort of computing it. So, but if you write this out, so essentially if you have something like n faculty and you apply this, so you roll out the definition, you get something like, well, you apply n, you with n times n minus 1 times n minus 2 and so on until you go to 1 and then you stop. Okay, so let's make a little calculation here. So what is the faculty of 0? What value does this take? Yes? No, if you take a look again, so we have faculty of 0 is defined as 1, right? So if you take the top row up there, so you can see faculty, so if this n is 0, then you get 1 up there, right? So this is 1. What is faculty of 1? Yes?
1.
Exactly. So we have, look at our definition here. So if we have, if n is 1, then we multiply 1 by faculty of n minus 1. Well, n minus 1 is 0, and we already know that faculty of 0 is 1. So you end up with 1 times 1, which is 1. So this is 1. So next, what is faculty of 2? Yes, 2 exactly. So again, we apply the rule, right? So now n is 2, and 2 times faculty of 1 gives us 2 times 1, which is 2. And next one? Yes?
6.
Exactly. So now we just multiply 3 with faculty of 2, which gives us 6. And the next one? Yes. Exactly. 24. And finally, faculty of 5 is? Exactly. So very proud of you. You know your multiplication tables. so now we understand how this thing is defined. And let me now just write it in a slightly different form that sort of is closer to what computer scientists would use to write down this function. So essentially, computer scientists, they don't like these curly braces here. They just write this using this if-then-else expressions. Okay, so this is just like another way of writing this definition. So I'm saying, and faculty is defined by this expression here, where I say, okay, if n is 0, then I'm going to return 1, and otherwise I'm going to return n times faculty of n minus 1. Okay, it's really just another way of writing down the same thing. And another thing I'm going to do is, I don't like this exclamation mark notations. I'm writing this down, I'm giving this thing a name. I'm just calling it fac. Okay, so fac of n is now defined by this thing here. So fac is sort of this stands for the faculty function. Okay. So now, what do we need to do to translate this sort of into a alligator and egg program? Okay, so there's essentially 3 things we need to do. First of all, we need to somehow represent this if-then-else. We need to write an alligator and egg program that sort of represents this if-then-else expression. Then, when we need to do somewhat, we need to be able to do arithmetic operation to actually compute with natural numbers. Okay, so we need to be able to multiply, we need to be able to do subtraction, and we also need to actually test whether a number is 0 or not. Right? So all of these things we also have to represent somehow. And then finally, there's this funny thing with this recursion, right? So we have a function that we define in terms of itself. And so we somehow have to deal with this also in our alligators and egg programs. So these are the 3 things we need to take care of. Okay. So let's see. This is the first sort of attempt to translate this into an alligator and egg program. So you can see this is actually not much that I did here. So I write the whole thing, this fact thing, as a single family, family of alligators. And you can see this is just, it has one hungry alligator at the top that eats another family that represents the number n. Okay, and then it's going to do some computation with that. And the computation that it does, it sort of exactly expresses what we have up here. Right? So it's this if-then-else. I represent this as a single alligator family. So this if-then-else. You can see it actually eats 3 other families. So we eat them like in a row. So and the first thing it eats is sort of this condition that we use to decide which of these 2 cases we're going to take. So this is essentially going to test whether, so this family is going to test whether this number is 0. And so if this is true, then we're going to return 1. So that's this case. And otherwise, we're going to return this here, which is represented again by this family here. So we have an alligator family representing multiplication of numbers. So it multiplies n with this stuff here, which is the faculty of n minus 1. So there's really nothing that happened so far. I just wrote this sort of in this form of the alligator and egg programs. Now, of course, what we really need to do now is we need to define these. We need to find alligator and egg programs that actually represent all these placeholders here, right? Like if and else, is 0, mouse, minus, and so on. And then at the end, what we also need to do is we need to get rid of this recursion. So you can see here we find an alligator and egg family, and this whole thing again appears here in its definition. And we cannot really do this in the alligator and egg program. So we have to have some way of writing this without using fac in the definition of the family. Okay, so let's start with the first thing, actually defining the alligator and egg programs that represent these placeholders. Okay, so in order to do this, we're going to use something that is called church encodings. So church has nothing to do with praying or so. That was a mathematician that used to do this in the 1930s maybe. And so he came up with this idea of how to sort of encode these things into these alligator and egg programs. And what we're going to do is, what we want to do is we want to represent this if-then-else thing. And so if-then-else is something that takes what we call a Boolean, which is like, it's a value that only has it's a type that can only take two values. Either it's true or it's false. So say telling us whether some test is true or false, right? So in our program we want to check whether n is 0, and we somehow have to represent the result of that test. And well, it can only take two results, either n is equal to 0, in which case the whole thing is true, or it's not equal to 0, in which case it's false. So we need some way of representing these truth values, true and false. And so you can see here are the actual alligator and egg programs that I'm going to use to represent these values. So the funny thing about the way we are going to do this encoding is that we actually use programs to represent numbers and values and so on. So essentially we can actually do computation with numbers directly by applying them, so letting them eat other stuff. Okay. And so here we have these truth values, true and false, and they're just represented by these families here. So now we just do understand how this works. So remember, we want to have something like this: if then else, 1, and say I have to do something. Sorry, this is some. This takes a value b, so b will stand for either true or false. So say this might be the result of testing whether n is 0. So that's sort of the result value, is either true or false, either this holds or does not hold. And then we return some values, say either 1 or 0. Okay. And so the way that this now works is, if you look at what we have at the definition up here. So the if-then-else is a family that first takes a b, like this, and then it takes values x and y. So this is our, this stands for our x, and this stands for our y. And then so if it eats these, so if-then-else eats a b, an x, and a y, and then what it's left with is just bxy. So if we apply the eating rule here, like 3 times, okay, then we end up with bxy. Now what continues to happen here depends on what b is. Okay. And in our example up here, so b essentially is either of this form or it's of this form. And what we want is that, well, if b was true, so if b is true, then at the end we want to just end up with x, right? So this gives us this idea that, well, if b is true, then we get x, and otherwise we get y. And so now if you see, well, true is just represented by this family here that eats an x and a y and throws away the y, just keeps the x. So if we put this here in, so this is our family that eats an x and a y. So if this is true, b is true, then we eat the x and the y, and we just end up with x. So let's make an example. So we have our true, which eats an x and a y, and just returns x. And we apply this to 1 and 0. So we let this eat 1 and 0. Okay, so if we do the eating rule 1 time, so what do we get here? Right, so now this guy eats the 1. So the 1 is going to go into the x, and it's going to, so this one is going, this alligator dies, and then the x is replaced by 1. Okay. So what we end up with is an alligator that still an alligator Y that eats a 0, and here is just a 1. And this is where we replace the X by the 1 which was eaten. And then the next step as well be, this guy eats the 0, but there's no egg corresponding to there's no egg of color Y down here. So all we end up with is just a 1. So this is another application here. That's exactly what we wanted, right? So we looked up here, so if B, and if B is true, we want to end up with X, which was 1. And so now you can see with false, what we have to do is we just do so the same thing. We eat an X and a Y, and now we throw away the X and only keep the Y. And again, if we do this here, so well, at this step, you would actually keep the 0 and not the 1 in the end, and so we just end up with the 0. Okay, so this is the way the if and else works. And now let's do some other more interesting stuff. So next, what we want to do is we want to next what you want to do is you want to compute the AND of two truth values. Okay, so essentially you want to check whether first the condition A is true and the condition B is true. So what this AND thing is going to compute is the following. I write this down in the table. Okay, so I have a value A, and this can take values either true or false, and I have a value B that also can take either true or false. And then what I want to compute is AND of A and B. So this is this family AND that's going to eat A and B, and A and B can take these values. And now, well, I have some combinations more here, so I can so we can have the combination where both A and B are true, and we can take the combination where both of them are false, and then we have to take the combinations where, well, A is true and B is false, and A is false and B is true. So then we have all possibilities of combinations of values that we can have. So let's see, we have true, false, and false, true. Alright, so what this AND computes is essentially checks whether both of them are true, and then it returns true, and in all other cases it's going to return false. So I'm checking whether both cases are true. So here I get true, and in all other cases I get false. Okay, so now what I want is I want to have a alligator and egg program that exactly computes this function. Right? I want to have an alligator and egg program, and here's my pointer. So I want to have this program and that takes eats an A and a B, and it returns true, so something of this form, if both A and B are true, and it returns false, something of this form if one of them is false. So how would this program look like? So now I have to sort of think of, okay, so if A is true, what do you need to do to get true if also B is true? And if A is false, what do you need to do to get false in the end? Well, essentially if A is false, it doesn't matter what B is, I always have to give back false. Any ideas what I should write down here so that I get back the right result in the end? It takes a little bit of thinking to figure this out. So let's say, I'll help you a little bit along. Okay? So let's say A is true. Okay, so then we know it has this form here. So it's something that expects an A, an X, and Y. And now whether the result should be, so if A is true, we know, okay, there's still a chance that we have to return true in the end, if also B is true. And if B is false, then we also have to get back false in the end, because they both have to be true. So you can see one thing we could do is we could take the A and let it apply as first argument to the B. Okay. So say we write down here A and B, and then so what we get is we have this true alligator here, true family, and it eats the B, and we end up with a family that eats the Y and always returns the B. Right? So then it doesn't matter what the Y is, it will always give us back B. That's okay, since well, if A is true and it eats the B, then whether we want to have true or false in the end always only depends on B. Right? So then if B is false, we get false, and if B is true, we get true, which is exactly what we want. So now the question is only what happens if A is false. So we need to have something else in addition. So we have to sort of write down three arguments. We have to write down A eats B and eats something else. So that we also get the right result if A was false. Okay, so and if A was false, it's of this form, and then, well, it doesn't matter what we, so it's going to throw away the B, and it will eat whatever else we give it, and only return that. And well, if A was false, we always want to return false, right? So no matter what, so here, if A is false, we return false in both cases. So, well, then what we have to do is, well, we can just let Y be false. We can have here A be false. Okay. So put this in. Just like this. So let's again do some computation that's actually returning the right result. So what we want to compute is say AND with, let's say, true and false. So what this is supposed to give us in the end is just false, right? So that's what we want to have in the end. Now AND is this alligator here, this family. So we have a family that eats an A and a B, and it takes the A and lets eat the B, and then it lets it eat false. And then we have true and false. Now what we can do is, well, we can let this guy, we can let the A eat the true and the B eat the false, and then we're just going to replace them down here. So this is going to give us, so we have to apply the eating rule twice, and what we end up with is the family where we have true, and then true eats false, and then false. Right, so this guy here went into the A, and this guy here went into the B. So we're going to replace A by true and B by false, and that's what we end up with. Right? So now we can see what is true. Well, true is the alligator, the family that eats an X and a Y, and just leaves the X. So let me just replace this here. This is just this family here. And now, so this guy here, we can let it eat false. And we can let it eat false here for the Y. And, well, the X here is just replaced by false, and that's what we end up with. Right, so this is again 2 times eating, and we just end up with false. And that's exactly what we want. Okay, so now what we want to have is want to have a family that computes an OR. Okay, so again it takes an A and a B. And now this is similar to the AND, but we want this guy to return true if one of the 2 is true. So if either A is true or B is true, then we want to get true in the end, and only if the 2 are false, we want to get false. It's almost the same as this guy, but slightly different. So does any one of you have an idea what I should write down? Let me just write the values in here. So this is what we want. This will be our OR. And now we get a true here. Here we get a false because both of them are false. And then in the other 2 cases where essentially anywhere where one of the 2 is true, we get true in the end. So we're checking whether one or the other value is true. And then we also return true in these cases. Any idea what this, what I should write down here so I can compute the right result?
So would it be AB true?
Let's see, that sounds promising. Let's see, so if we have an A, let me just write this down as a candidate. A, B, true. So let's see, if A is true, then we always want to return true, right? No matter what. So you can see here if A is true, in both cases we return true, and it doesn't matter what B is. And so if A is true, it's of this form, and then which means it eats first the B, and then returns the B, and it eats the true, and it throws away the true. Okay, so we just end up with B. But now the problem is, well, if B is false, then the end result will be false and not true. So it's not exactly the right thing that we want, right? So essentially, if A is true, we always want to return true. And only if A is false, then it depends on B what the result will be. So actually, you almost got it right, but we sort of have to switch the order of the arguments. Right? So we first let it eat true, and then we let it eat B. And now it will work out, right? So now we can see, well, if A was true, it eats true and B, and it should always return true, which it does, right? Because X is going to be replaced with true, which is the right thing. So then it doesn't matter what B is, it will always get the right result. And on the other hand, if A was false, well, we eat true but throw it away, and we eat B and just return B. And now, well, if B is true, we return true, and otherwise we return false. So only if both of them are false, we actually end up with false in the end. So this will give us the right value. Yeah, but very good. So we almost got the right result. So now, the last thing we want to do is you want to have a function that takes a value true or false and just gives you the opposite value. Right? So if it takes true in, it should return false, and if it takes in false, it should return true. So I'm just writing this down myself. And so this is a little bit more complicated in the sense that now what we need is, we need to write this down as a new Boolean value. So we need to write this down as a family that takes an X and a Y and then does something so that we get back the right result. So we have a family that takes an X and a Y. And so what should I write down? So I now can use the B, the X, and the Y down here. And I'd have to use them in such a way that well, if B was true, this whatever I have here should reduce to X. And if it was false, it should reduce to y. So then in the end I get either true or false here. So what should I write down here? So I can sort of use b to compute the right value here. So let's see again. So yeah, b can be of this form, or it can be of this form. Right? If it's of this form, well, I can, for instance, let it eat the x and the y, and then it would return the x. Right? So then altogether I would have this family that takes an x and a y and returns an x. But that's true, but what I wanted to have in the end was false and not true. So I need to do something slightly different to get the right result. So say, let me just write this down again. So I have the b, the x, and the y. So what I get now is, so say I eat true, and then true eats x and y, and it throws away y and just leaves us an x. This whole thing here just represents x if b is true. So I get a family that eats an x and the y and returns an x. So that's true. But what I wanted is the opposite, right? I wanted to get false in the case that b was true. And also, well, if b is false, then it's going to eat x and y, and it's going to throw away the x and just leave me y. So then I have a family that has an x and a y and just returns a y, and that's my false. So if I eat a false, I get back a false, and if I eat a true, I get back a true. So this thing doesn't do anything right now, it's over the down. So what do I do is just a small change such that I get the right results. And if I eat true, I get false, and if I get false, I get true. Any idea what I need to change? You have an idea? Exactly. So if you can see, if I switch these two around, then I get exactly the effect of sort of swapping true and false. So let me write down y and x here. And now you can see, well, if b was true, right, it's of this form, it eats y and x, and it returns y. Right, so it eats a y and an x, and it returns the first guy, which is a y. So altogether I get a family that eats an x and a y, and just returns the y, which is our false. So if b is true, I get false in the end. So that's exactly what I want. And now if, on the other hand, if b is false, then I'm eating the x and the y, so I'm eating 2 and throwing away the first one. So I'm eating y and x, and I'm throwing away the y, just keeping the x. So I get a family that eats an x and a y and just gives me back x, which is true. So if I eat false, I get true. So that's exactly the right thing. Okay, so this was a nice warm-up. So now let's see how we do numbers. How do we actually do computations with numbers? Okay, so now we need some way of actually representing numbers in our programs. So we need some way of, I mean, you all know so the symbols to represent the natural numbers. So you have 0 to represent the number 0. You have, well, this symbol here represents the number 1, and so on. So these are just representations of numbers, just like we could, for instance, use Roman numbers to represent the same numbers. So these numbers, these ways of representing numbers, they're called numerals. So you can think of them just as a way of representing the mathematical objects that are numbers. Okay, so these are the our standard numerals that we will use. And so what we will do now is we will come up with another way, another kind of numerals where we use alligator and add programs to actually represent numbers. And the trick here that we're going to do is we sort of represent numbers by using these two functions here. So we have a function, or this is actually just the z here just stands for the number 0. And then we have this function here that takes a number and adds 1 to it. So we call this the successor function because it gives you the, given a number, it gives you the next larger number. So if you give it a 1, it gives you 2. If you give it a 3, it gives you 4, and so on. And then this is sort of the way we represent numbers. So we have 0 is just z, and 1 is successor of z, and 2 is successor of z. So you sort of need, if you have the number n, then so you sort of take n times the successor function of z. It's just another way of, you think of this as a way of computing the number just by adding 1 starting from 0 n times. Okay, so now we're going to use this idea for representing numbers using alligator and axe programs. So here is our, so all the numbers are represented by families that where we have an alligator that eats an S and an alligator that eats a Z, and then does something with that. Maybe what it does is it sort of it sort of puts S. So if you have, say, in general, if you have a number n, we sort of let S n times eat itself and then eat the Z. So that's sort of what we're doing. So if you have, in the case where it's a 0, we just return Z. If we have a 1, well, we let S eat Z, so that gives us 1. Then if we have 2, well, we let S eat 1, which is sort of something which is exactly S eating Z, and so on. Right, so you can now give me the representation of 3. So who has an idea of how the 3 will look like? Yes? Like this, right? Exactly. So you can see how this pattern continues, right? We just add another bar on top and let S eat what we had before. Okay, so now we want to actually compute with these values. So now, for instance, what we want is you want to have an alligator and egg program that takes a number n and then gives us the next bigger number. So it's like adding 1 to the number. So for instance, if n is z, is 0, then we should get back 1 in the end. And if n is, say, 1, we should get back 2. If n is 2, we should get back 3, and so on. Okay, so let me just speed up a little bit. So I'm giving you actually the results here. Okay, so let's see. How would we do plus 1? Well, we have an n, and we need to get back something of this form that takes an S and a Z. So I'm writing this down like here. And then, well, what I do is I let n eat S and Z. So this gives me the number n, and then I just add another S on top of it. So now I have, so you can see if n was this guy here, it eats the S and the Z, it throws away the S and just returns the Z. So this would reduce to Z. And then what I get is S eats Z. So I'm getting an alligator that takes an S and a Z and then just applies S to Z, which is 1. And then the same way we would get, say if n was 1, we would get 2 in the end. If n was 2, we would get 3 and so on. And so here's another thing, say where we want to compute plus, so where we eat an m and an m, and then we want to get the number that represents n plus m. And the way we could do this is, for instance, like this, where we say, okay, I mean, you can always think of these numbers as something that does, so the number n is a program that does something n times. So the number n is a program that does something else n times. So if you write something like n and let it eat plus 1, it will do plus 1 n times. And it will do this to the second argument, which is an m. So what we end up in the end doing is we take m, and then we add 1 to it n times. So in the end, what we get is n plus m, which is what we want. And so similarly, you can do multiplication this way. And also what you can do is you can actually sort of implement our zero test. Right? So we can write a family that takes a number and then returns true if n is 0, and otherwise it returns false. So you can see here if n is 0, it eats this guy and it eats this guy, and it throws away the first and just returns the second, which is true. Well, then that's exactly what we wanted. Since n was 0, we return true. And if we have some other numbers, say we have 1 here, so if n is 1, then we're going to eat this guy and this guy. And so then what we do is we take this guy and then it eats this guy, so that's as like to see. And when this guy eats true, so true goes into x, then x is going to be thrown away, so we just end up with false, which is also what we want. So it's, 1 is not 0, so then the whole thing gives us false. So this is 0 gives us back true if and only if this n here was 0. In all other cases it would be false. Okay, so I'm skipping over the subtraction. It's a little bit more complicated, but there's also a way of sort of computing n minus 1. So if you have a number n, then we can actually write a program that takes a number and returns as a number that's n minus 1. And that's essentially all we need for our representation here. So we have the 0, we have the else, we have multiplication, and we have minus 1, or minus in general. So essentially, we are almost done with our program, and all we need to do, all that's left to do is we have to somewhat get rid of this factorial here. Right? So we're defining the program using the program itself, and we cannot do this in these alligated act programs. Right? We cannot say we have this family and this family occurs within itself. So somehow we have to get rid of this. And so here is a nice trick how to do this. Okay, so I'm just rewriting our program a little bit. So instead of defining this directly, what I'm doing is I define a new function. This is this rad fact here that takes another function as input. Okay. So the trick is, it's like, think of this like this. Okay, you want to compute the faculty function, and you know how to do it for one step. Okay, so essentially, if someone told you, so you want to compute for number n, and if someone told you how to do it for n minus 1, then you know how to do it, right? You just multiply the result by n. So essentially, if you ask someone else and do it for you for n minus 1, you know how to do it for n. And that's sort of what this function represents. It's like someone else tells you how to do it for n minus 1. So you can compute the faculty of n minus 1, and then all you need to do is just multiply it by n. So how does this help us? Well, now we can sort of use this to approximate the actual faculty function. Right? So we can start off saying, okay, we have a function that we call this fact0. It always returns 0, no matter what n is. And, well, you know, the actual faculty function never returns 0, so this always gives us the wrong result. Okay, no matter what. But now, well, you can define fact1 in turn by sort of applying to this rad faculty the fact0 and n. And well, now, if you sort of look into the definition, well, if n is 0, we return 1, which is the right result. Right? So for if n is 0, we get back the right result. And in all other cases, we get the wrong result. Right? Because in all other cases, we just get back 0. But for one value, we already have the right result. Now we can just go on like this, right? We can do fact2 and just put in the fact1 here, and then we get the right result for 1 and 0. And in the next iteration, we get for 1 and for 2, 1 and 0, and so on. So if you do this n times, then we get the right result for all smaller numbers. So if we sort of this fact I, so if you did this I times, then essentially for all smaller values in I, we get the correct result. So now the trick, what we need to do is we need to somehow get sort of some family that does this kind of doing something arbitrarily often, right? Sort of recursion. And it has something that takes a program and then So if we say we want to find this this family called fix, and it takes another program, say fact here, and what we end up with when we do this eating is this thing here. So we have fact that eats this fix of values, which is what we started off with. And if we continue to do this again here, we get now fact of fix of fact, and so on. So this will give us exactly this kind of approximation that we had. So think of this as the first step. This is sort of the this itself is the approximation where we always get the wrong results. This is the one where we get the right result for 0. This is the one where we get the right result for 1, for 2, and so on. And so there's actually a way of writing this out. So I mean, it takes a while to come up with this, but I won't go through this now because I'm running out of time. But what you can do is you can just plug this program here in this fix here, and really just compute this eat and eat, and you will see you end up with exactly this thing here. So you're really doing the right computation. And so this is essentially all we need to do. So now for computing our factorial function, you can define this fact as our program here, where we now take this additional function that we eat, and then the actual factorial function is, well, fix of fact and then. That's our alligator and add program that's going to compute the factorial function, the factorial for the natural number n. Okay, I'm going to stop here. But the point I want to make is, so why did we all of this, these funny computations? And so essentially what I explained to you, this alligators and eggs programming language, is something that computer scientists call the untyped lambda calculus. It's another funny name for the same thing. And this untyped lambda calculus is really what modern programming languages use for doing computations. Essentially, there's a whole bunch of actual programming languages that are based on this calculus. They're really the way these programming languages do computations is exactly by applying these rules: the eating rule, the coloring rule, and so on. And I can even show you an example. So this is all these encodings that I showed you in this lecture, written down in one of these programming languages. And so this lambda here, you can think of this as the hungry alligator that eats a x and a y and returns an x. So that was our definition of true. So the run is, this will just give us all the functions, and I'm going to write the faculty of the number, let's say 3. And I compute this, and I really get back the right result. So you can see this, what this program here is doing. It's doing exactly these computations that we defined on the previous slides. It's really computing the faculty functions exactly in the way we did it in our encoding. All right, so let me stop here. And so here's some credits. Specifically, I mentioned Alonzo Church. So he was the guy who actually came up with this lambda calculus. So this is essentially, you can think of this as a universal programming model that you can use to think about what programs actually do in computer science. Okay, so I'll stop here, and I hope you have a nice day and enjoy your lunch.
You too.
Thanks.